funky in only the good ways. So, the table reads scores from 90 to 99. 4 students scored in that range. 80 to 89, 8 students scored in that range. 70 to 79, 12 students. 60 to 69, 4 students. And finally, 50 to 59, 2 students. And what we want to do here is we want to find the mean and the standard deviation. First off, we have to compute the mean in order to do our standard deviation. Do you all agree? Given our formula that we had last time, totally. We have to compute our mean. Now, in this problem, our standard deviation, no pun intended, is not really going to take on a whole heck of a lot of meaning. The reason why is because it's just, you'll see what we get. We're going to get like 10 point something. And it doesn't really take on a lot of meaning because we don't really have anything to compare it to. Okay? We'll discuss that momentarily. Now, why did I say that this guy's kind of funky? Well, first off, if we are going to compute our mean and our standard deviation here, don't we need a probability distribution table? Yeah. Do we have a probability distribution table here at this point? No, we totally don't. Okay? So, this is one of those situations where first we're given our frequency, and then what we can do is compute the probabilities. So, that is one kind of funny little place here. So we've got to compute our probabilities first. Now, let me say something here. I claim that we have done this before. When you're given your frequencies, can you compute your probabilities? Absolutely you can. Okay? Remember, the probability of an event is the number of ways that can happen or that does happen divided by the total number of ways or the total number of people. So, for example, what is the probability a randomly selected student scores in the range from 90 to 99? It's 4 over 30, right? 4 people did it out of our total 30 students. You with me that far? Okay? What's the probability that a randomly selected student scores in the 80 to 89 range? Isn't that 8 over 30? You guys with me? Okay, what's our probability here? 12 over 30, then 4 over 30, and then 2 over 30. Tell me something. If you added the number of students, do you agree you would get 30? And if you add all of those probabilities we just did, do you agree we get 1? Okay, so life is working well so far. Any questions this far? Okay, that was one little funky piece. Another funky piece comes when we say, well, let's compute our mean. What is the mean called when we're looking at a probability distribution table? Expected value, good. And I'm not sure whether you remember your formula. You had to use it yesterday. But do you guys agree the formula for your expected value is you take your first x value times his corresponding probability and add that up going down the line? Yeah. All right. So we look at this table and we're like, oh boy, right? We got a range of scores here, 90 to 99, 80 to 89, etc. So you may ask, what do you do? Well, your book gives you the hint, but I also wanted to do this in class. What you do is you take the middle value in each range, okay? So between 90 to 99, I would take my x value to be 95. 80 to 89, I would just take it to be 85. Then 75, 65, and 55. estimate for our mean, but it's the best we can do. Are there any questions this far? Okay, so the reason why I picked this example is precisely because of those two little funky situations. Number one, you got to take the middle of the range, and number two, if you're just given your frequencies, you need to then first compute your probabilities. Everyone with me? Okay, now let's find our mean. Well, our mean is, you take your first x value, 95, times his corresponding probability, which we found to be 4 over 30, plus your next x value times his probability, which is 8 over 30, and then we have plus 75 times 12 over 30, plus 65 times 4 over 30, and plus 55 times 2 over 30. Now, I know that this looks nasty, and this is one reason why I already promised you guys, if you ever have to do like mean and standard deviation of a probability distribution table, it's going to be a pretty small table, okay? But fortunately, it's not too bad to, this is where we're going today, but anyway, it's not too bad to plug into your calculator, okay? I mean, literally, you can punch that in without any parentheses. 95 times 4 divided by 30, plus 85 times 8 divided by 30, plus 75 times 12 divided by 30, plus 65 times 4 divided by 30. I gotta get a life, you guys. I know all these numbers by heart. And ta-ta-ta-ta, we get 77.6 for the mean. Now, what I would say, since we're just dealing with test scores, I would conclude from here that our mean is 78. I would just round to the nearest whole number. And I would tell you to do such in a similar situation. Are there any questions this far on the mean? Okay, so that's about what we could predict our average test score to be. Okay? Again, it's definitely an estimate because honestly, we don't really know how many scores fell at the top or the bottom of each of these ranges. Okay? Alrighty. Well, now we get to compute the standard deviation. I know it is a royal pain to compute the standard deviation. That's why we're just going to do one more. And that is also why I said it's on next week's quiz, and then we're cool. Okay? So, recall the formula for your standard deviation is the square root of the first probability times the first x value minus the mean squared, plus the second probability times his x value minus the mean squared, and you take that all the way across. The x bar at this point means the mean. And this is still all over that red. Nice to have two overheads, huh? All right, that's our formula. Again, you don't have to memorize such a thing. When I will ask you to use this formula, the table won't even be this big. Okay? So, can we compute our standard deviation? We absolutely can. We have all of our probabilities. We have all of our x values, and we've now computed our mean. Correct? So, I'm going to slide this guy back down so that we have all of the information we need. If you want to write this out in formula form first, this is what you would do. You would take your first probability, which is 4/30, your first x value minus the mean, which we found to be 78, and then square that. You guys remember this from Wednesday? I hope. Plus your second x, or your second probability, excuse me, which is 8/30 times your second x value minus the mean, and you square it. Plus 12 over 30. Then you take 75 minus 78 squared. Well, you guys have this in your notes, so. Okay, so we'll continue the radical. Plus what? It was 4 over 30, 65 minus 78 squared, plus 2 over 30, 55 minus 78 squared. And this whole thing is under that radical. Now, if you're thinking, ew, I am too. All right. You will be glad to know when we start the next section, which talks about binomial distributions, your mean and your standard deviation are like very quick, cute little computations. So, you guys ready to plug this into our calculator? Yeah, I'm about that ready too. All right, so let's do it. Now, the nice thing is we don't have to do this by hand, right? Our calculator at least does the dirty work. So, here's what we do. You hit your square root button. Notice, I automatically have a parenthesis that shows up. If you don't, put one in. And literally, you're going to type it as you see it. 4 divided by 30, now you put parentheses. 95 minus 78 squared. Plus 8 divided by 30, then put your parentheses. 85 minus 78 squared. Don't forget to close your parentheses before you square anything. All right, plus 12 divided by 30, 75 minus 78 squared. And you guys can read this and go on down the line, so you don't have to hear me say it all. And my last comment will be this. I typed in all of that information. I have to then put another parenthesis to close my first one. Some calculators are very particular and you'll get an error message and be like, oh my God, I gotta type that whole thing in again. So might as well play it safe. And we hit equals, yep, 10.63. There you go. Are you thrilled? Now, in a data set this small, this tells me my data is fairly spread, but we don't really know, relatively speaking, how spread out it is unless we had another standard deviation with which to play with. Yeah. Oh, you can do that too. You can first do that division and get a decimal if you want, and then plug that in. Absolutely. I'm lazy. That's just the best way to put it. If you do that, you should get the same answer, and it's worth checking out. Okay? Are there any other questions? All right, you guys ready to start section 8.4? This is a fun one. I mean, maybe you think all of this is fun, but yeah. Okay. This next section is called a binomial distribution. I claim this stuff is really fun. Just letting you know that right from the start. And let's talk about this. We haven't talked about probabilities getting this complicated yet. I've intentionally avoided it. Now, on the positive end, these are really easy to compute if you have your calculator. So definitely keep your calculator out. I'll show you how to push the appropriate buttons. Okay? But let me talk about when you would use such a thing. Okay? Because you need to know when you would compute probabilities in this manner. So first what I'm going to do is give you the 3 criteria that need to be met in order to compute these, in order to talk about computing it with a binomial. And then what I'll do is I'll give you a ton of examples and a ton of hints as to how to know when you're reading a probability problem, how do you know if it is, say, binomial versus the combinations that we've already played with, etc. Okay? So, you use this when, number 1, an experiment is repeated several times. 2, there are only 2 possible outcomes. All the textbooks call them success versus failure. I'll show you soon enough why I don't really like that terminology. But it's really just a nitpicky thing. And number 3, each trial is independent of the others. Don't worry, you will not have to compute the independence here. Okay, so what are some examples of situations where we have a binomial distribution? Well, I claim one of them is flipping a coin. Yes, we know the probability of getting a head is 1/2 and the probability of getting a tail is 1/2. But this is also an experiment we could repeat multiple times. You agree? Okay? So it meets the first criteria. The second criteria, there's only 2 possible outcomes. I think you'll grant me either you get a head or you get a tail. Yes? And presumably, if this is a fair coin, each time you flip the coin, whatever turns up is independent of what happens the next time you flip the coin. You all with me there? So do you see how it meets these 3 criteria? Okay? Another one that may not seem as obvious at first, but let me explain, is rolling a fair die. Do you agree you can roll a die as many times as you would like? Yeah, so we can repeat that experiment many times. Now, I know you're all thinking, well, wait a minute, Lauren. It's a 6-sided die. Well, what you then have to do is define what a success is. So we can say that a success is rolling a 2. So now will you grant me that there's only 2 possible outcomes? Either you roll a 2 or you do not roll a 2. Y'all with me there? All right, and last but not least, again, presumably it's a fair die. Each time you roll the die, what turns up is independent of another time. Okay? Now, another common problem that's done using binomials, and this is where my problem with number 2 comes out, is having kids. And anyone who's a parent definitely agrees that having kids is an experiment, right? In only the most beautiful way. Okay, but you can repeat that experiment several times, right? You can have more than 1 kid. Yes? This is where I don't like it, okay? Yes, there's only 2 possible outcomes. Either you have a boy or a girl. Well, it's kind of sick to define one as a success and the other as a failure, right? So that's where I have the problem with the success or failure business. But I think you'll grant me that there's only 2 possible outcomes.
You have twins that win the boy and the girl.
Yeah, let's talk about single births. You are exactly right. And then you hope you don't repeat that experiment several times, right? Holy moly. All right, and then presumably, each time you have a kid, whatever sex it is one time is independent of what happens the next time. Okay? That's a common one. I'm only bringing it up because you'll see examples in your book, and I also wanted to explain why I hate the success-failure business. All right, another one, say, is taking a poll. Okay? You can take a poll on what candidate somebody might like. Well, you can go door to door, and therefore you can repeat that several times. And I think you'll grant me either they like the candidate or they don't like the candidate. So there's only two possible outcomes. And last but not least, if the person at this address happens to like the candidate, their opinion is completely independent of what their neighbor's is, typically. All right. Now, how will you guys know that you're in a situation of a binomial distribution? Well, number one, on your quiz next week, I'll actually come out and tell you assume a binomial distribution. Okay, so that is very much one obvious way if I tell you, correct? All right. Now, and the reason why on the first quiz I will definitely fill you in on that is because I'm going to want to know, hey, do you know how to compute binomial probabilities? All right? Now, another really good indicator as to whether or not you're in a situation with a binomial distribution is if there's a general percentage given. Okay? If a percent is given, you can assume it's going to be a binomial situation. I will show that to you momentarily. Okay? Again, as with everything else in math, for better or for worse, it all comes with practice. Okay? So, let me take an example to motivate this. And what I'm going to do is I'm going to motivate the formula that we used to have to use before our calculators could compute it. Some people still like to do this way, but then I'll show you the quick and easy way on your calculator. Okay? So, here's our scenario. Suppose a fair die is rolled 12 times. And what we want to do is find the probability of rolling exactly 5 twos. Now I claim there's more going on than meets the eye. And don't worry, I'm going to break this up. Okay? First off, maybe you're thinking, well, wait a minute, Lauren. What's so difficult here? What is the probability of rolling a 2? It's 1/6, isn't it? You guys all agree? Great. And while we're on the situation, what's the probability of not rolling a 2? Isn't that 5/6? Now, do you guys agree that this is the complement of my first line? And so couldn't we get that 5/6 also by taking 1 minus 1/6 to get to 5/6? Okay? So maybe you're thinking, okay, I know these probabilities, what's the problem here? I mean, don't we want a 2 happening 5 times? So don't you think you would just take 1/6 times 1/6 times 1/6 times 1/6 5 times? Right? Remember, we're rolling this die 12 times. So, do you agree instead of writing it out 5 times, it's easier to write 1/6 to the 5th? Exponents are not meant to be confusing. They're lazy person's good friend, I suppose. Okay? Now, listen, you guys, if I want exactly 5 2s, but I'm rolling my die 12 times, how many times will I not get a 2? I'm rolling my die 12 times. I want to get a 2 5 times. So how many times will I not get a 2? 12 minus 5 or 7. So that's going to happen 7 times. But I claim that we're not done. Okay? You have to take into account the total number of times you're rolling that die. Now, you might ask, well, what else do we have to think about? Well, not only do we need to deal with each trial, I'll write this out, do we need to find the probability of each trial, which we have done, right? There's a total of 12 trials. We wanted 5 of them to have the probability of 1/6, and 7 of them to have the probability of 5/6. But we also need to figure out all, this is the key, possible combinations of where in those 12 trials the 5 2s occur. I mean, there's a lot of different possible ways that can happen, right? Maybe you get a 2 the first 5 times you roll your die, and then you get other things the last 7 times. Maybe you get a 2, then not a 2, a 2, then not a 2, etc. So do you guys agree we also have to figure out in how many different ways we can get where those 2s appearing in our 12 rolls? What's the key word? I underlined it. Combinations. How many times are we rolling our die? 12 times. How many times are we interested in the 2s happening? 5. So in general, that's actually how you would have to compute it. We're not going to be computing it that way unless you want to. I will give you the general formula momentarily. Okay? But what I want to say to you guys is this. Okay? That not only do you have to take into account in all the different ways you can get 5 2s, but then you also have to take into account the probabilities. Let me give you the formal definition. I know it involves a lot of letters. I will liken each letter to what we have over here. And then what I'll do is I'll show you the quick and easy way on our calculators. Okay? And then we'll do one more example and call it good for the day. Okay? So, for our binomial probability, if P is the probability of success, and 1 minus P is the probability of failure, okay, so I'm already going to bebop over here. I claim my P here is 1/6, right? We wanted exactly 5 2s. And the probability of getting a 2 is 1/6. Do you guys agree that the probability of failure is 1 minus P? So 1 minus 1/6 here was 5/6. See? Right? Now, what does it say? It says for n independent trials, with x successes and n minus x failures, don't worry, I'll go through that. The probability is n choose x, p to the x, times 1 minus p to the n minus x. So let's mosey on over here. For n independent trials, in this example that we did, how many times did we roll the die? 12 times. Isn't n equal to 12? You with me here? You always have to be given that. And notice my n here is 12. You with me that far? Now, how many successes are we interested in? How many times did we want to roll a 2? 5 times. So in this example, our x is 5. Notice there's that x here, and there's that x up here. Okay? Now, n minus x here was 7, right? If I'm rolling it 12 times and I've accounted for 5, 7 is the rest of them. And that's where I have this exponent to be 7 here. Now, just a couple cute little things I would like to point out to you. Following. Notice my exponent here matches this here. Also, if I add 5 and 7, don't I get my total of 12? Yes. Now, you guys are probably feeling pretty like, okay, Lauren, let's be pragmatic. How do you compute these in our calculator? Well, this formula will also be given to you on a test. This formula will be given to you, okay? You need to be able to identify your n, your p, and your x. So, for this example, everybody take out your calculator. I'm going to show you how to do this. So I look at my calculator, and I've got an arrow up, arrow down, arrow left, arrow right. And then I look underneath, and I have my clear button. And then I look to the left of it, and I have a button, and my button says bars. Do y'all see that, bars? Bars. But above bars, it's going to say district. Now, you might have a different calculator, in which case you will need to access your manual to find out where this is. Okay? But we're talking about a binomial distribution, so district is where we want to be. So, how do you get to district? You hit second bars. You good there? Cool. Now, we will be dealing with these normal guys next week. But let's cruise on down. And we will be dealing with binomial CDF later. But today, it's binomial PDF. The way you put this in is you have to identify in the particular problem that you're working on, what is your n, what is your p, and what is your x. So, in this dice example that we did, what was our n? How many times did we roll the die? 12 times. Put a comma. Comma's above the 7. What was the probability of rolling a 2? 1/6, so put 1 divided by 6, comma. And how many times did we want a 2 to happen? 5 times. Close your parentheses, and there's your probability. How totally sweet is that? Yeah? Now, you might have a different calculator, okay? Your calculator might say trials, p, x value, pace. That means you have a nicer calculator than me. So for trials, you put in your 12 and then hit enter. For the p, you put in 1/6 and then hit enter. For your x value, put in the x value, hit enter, and then just keep hitting enter until it gives you the answer. Sweet! Let's take another example. Ready? drug cures 85% of the people who take it. The drug is given to 20 people. Let's find the probability for the first guy. Let's find the probability exactly 18 people are cured. Now, we might not get to every part of this example today. We might have to continue it Monday, but that's fine. All right. I claim number one, this is a classic binomial situation. Okay? An experiment is repeated several times. Yes? In fact, how many people are we giving this drug to? 20 people, right? So, n is equal to 20. Y'all with me there? All right, next. There's only two possible outcomes. Well, either the drug cures the person or it does not cure the person. And number three, they say each trial is independent. Will you grant me that if Paul is cured, that's totally independent as to whether or not Susie is cured? Okay? So, this is a classic binomial situation. Another way to read into that is, let's call being cured a success. I think that makes intuitive sense. What is the probability of success? 0.85. We got it right here. Okay? So, the way we would compute this is we would say binomial PDF. What is n? 20. It's our total number of people. What's the probability of success? 0.85. And how many people are we interested in being cured in this particular situation? 18. Throughout all parts of this example, you guys, your n and your p are not going to change. The only thing that's going to vary are your x values. So, let's do it. I hit second bars, I'm in district. I go down to binomial PDF, and I'm going to hit 20, comma, 0.85, comma, 18. Close my parentheses, and it's about a 23% chance. These aren't bad to compute once you know how to push buttons, huh? Okay? Everyone okay with this part? All right. Next one. Now let's find the probability at least 19 people are cured. All right. Remember the whole at least, at most, no more than, no less than? It doesn't leave us, you guys. Okay? In the context of this problem, what does at least 19 mean? 19 or 20, correct? So what this means is we're actually going to have two binomial PDFs to compute. Okay? Right? Binomial PDF, n is still 20, p is still 85.85, my x here is 19. What does the or tell me in terms of operations? Plus, good job, binomial PDF, 20, comma, 0.85, comma, 20. Are you guys with me there? Now, you can enter this as one long strand. You just hit second bars, go down to binomial PDF, 20, comma, 0.85, comma, 19. Close that parenthesis, and then do plus, and then just hit second bars again. Isn't it great that our calculators are good multitaskers? I think so too. And so we get approximately 0.18. are cured. Oh my gosh, in the context of this problem, what does at most 16 people mean? It means 0 or 1 or 2 or, oh my gosh, all the way up to 16. Do you guys want to compute 17 binomial PDFs? Neither do I, okay? But this is where the binomial CDF comes in. Let me write this down. So the binomial PDF you use when you want to find the probability at a point. The binomial CDF does the probability from 0 to that point. In other words, when you have an at most, it's cool. All right, if you want to try this weekend, I mean, I'd say I'm giving you a fun thing to do this weekend, but it's really not. Do all 17 binomial PDFs. Add them together, you'll see you're going to get the same answer. Okay? But the binomial CDF looks at a whole range. It starts at the bottom and it goes through that. So don't freak out when you see it most. It's actually kind of a sweet situation. So the way I would do this problem is I would hit binomial CDF. My n is still the same. My p is still the same. And we want at most how many people to be cured? 16. That sounds kind of mean to those other 4, huh? But that's all you would need to plug in. So let's do it, because we really need to know the answer. So now bow down to binomial CDF and plug it in. And there's about a 35% chance. Are you guys okay this far? We'll play some more on Monday. In the meantime, hold on one quick comment. Number 1, have a lovely weekend. Do something fun. Not that